Hi, in this video, we will talk about related rates, okay? In the related rate problems, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity, okay? The procedure is to find an equations. This one is the one that a lot of students struggle, okay? Is to find the equations, okay? That is from application problems, okay? That relate the two quantities and then use the chain rule to differentiate both sides with respect to time. Okay. So then first, we would like to learn how do we actually take the derivative with respect to time then. Okay. The idea is really similar to the chain rule that we have learned before. Okay. So for example, if I want to take the derivative of x squared with respect to t, okay? So in this case, you will see that the derivative of x squared, it will be 2x, okay? But x is my inner functions. So again, I need to take the derivative with respect to t of x, right? So this is what we want to do, okay? And so therefore, the result that I have, it will be 2x dx dt then, okay? Okay. Now, one thing about this is some student, they would like to rewrite the dx dt to x prime, okay? Because it's the derivative of x, okay? However, I don't want you to actually do it this way, okay? The reason is some of the students, when they see x prime, they feel that, oh, it should be 1. But again, you see that in this case, it's not 1, right? Okay. So therefore, try to avoid these notations. Okay. Okay. And now let's try the next example. Okay. To this one, again, is the sum. So therefore, I would like to take the derivative of x squared with respect to t. So I have 2x dx dt. And then we would like to add, okay, the derivative of y to the 4, it will be 4y to the power 3 dy dt. Okay. Then be careful about this. This one will be x squared times y, which is a product rule. So again, if you remember, top product rule is f prime g plus f g prime, right? Okay, so let's see how we take care of this. So now I would like to take the derivative of x squared with respect to t times y plus x squared times the derivative with respect to t of y, okay? Okay. Then now you will have 2x dx dt y plus x squared dy dt. Okay. Usually we like to write the dx dt to the end of each term. So I like to rewrite this into 2xy dx dt plus x squared dy dt then. Okay. Okay, so let's see how we take care of related rate problems now. How do we solve it? Okay. Now first, we need to read the problem carefully. Okay. And then we would like to draw a diagram. Okay. And the next is we would like to introduce, okay, the notations. So again, we would like to assign symbol to all quantity that are function of time. Okay. And now we would like to express the given informations and the required weight in terms of the derivative. Number 5 is the one that we would like to write an equation. This is the hardest part, okay? Then relate the various quantities of the problem. If necessary, use geometry of the situation to eliminate one of the variable by substitutions then. Okay. This problem we will again, for problem number 3 and 4, then we will use it then. And then now we would like to use the chain rule, okay, to differentiate both sides of the equations with respect to time. Okay. Then the last step is we substitute the given informations into the resulting equations, and then we are going to solve the unknown weights. Okay. Okay, so Now the common mistake, a common error is to substitute the given numerical information too early. Okay. So this should be done only after the differentiations. Okay. Now a lot of students actually they again substitute the given numerical information before they take the derivative. So therefore, this is actually try to avoid this. Okay. Actually, not to do this. Okay. Then let us look at our first example now. Okay. Let's see how we follow the again the 7th step to help us to finish the problem. Okay. Then now it said that the length of a rectangle is increasing at the rate of 8 cm per second, and the width is increasing at the rate of 3 cm per second. So now we need to work with a rectangle. So why don't we draw a rectangle first? Okay. And then we have length and width. Okay. Now this is actually the time that we would like to, again, when we introduce the notations, okay, so we are going to assign it. Then in this case, of course, if I assign L, then to add to the length, and then the W, then we know that is we assign to the width, right? But what if you're using X and Y? Then now you have to tell me that what X and Y are, okay? So normally we can do that. We can do this then. I would like to write down let L be the length of the rectangle. Okay. And we would like to let W be the width. And then let us look at the rest of the problem now. And when the length is 20 cm and the width is 10 cm, how fast is the area of the rectangle increasing? Okay, so now we mentioned area, so maybe we could let A be the area. Okay. Then now, what information do I have now? Okay, so let's see what are the givences then, what we have. Then first of all, we have the length of the rectangle is increasing at the weight. Now, you see, when you see this statement, I know that somehow it is related to the derivative now, right? So in this case, it's telling me that the length is increasing at a rate of x cm per second. So in this case, we could assign x cm per second equal to dl dt. Okay. Then now the width is increasing at the rate of 3 cm per second. So in this case here, then I know that I will assign dw dt is 3 cm per second. Okay. So it seems that those are the given information. So I have dl dt is x cm per second, and dw dt, it will be 3 cm per second. Okay. And then now, what we are looking for, we would like to find how fast is the area changing. So meaning we are looking for dA dt is equal to what? When L equal to 20 cm, and then W equal to 10 cm. Okay. Now you will see that those are kind of like the given information, right? Okay. And now let's see how we actually work it out the problem. Okay. So to this one, we are done with 1, 2, 3, and 4. Okay, those steps. And then now we would like to work on step number 5 now. Okay. To this step right here, we would like to write an equation. So meaning now we need to create the equations or the formula, right? What formula that we would like to create? In this case, we are looking for the area of the rectangle. So then now we know that the area of the rectangle is A times LW now. Okay. And now we would like to work with the step 6. We would like to use the chain rule to differentiate both sides of the equation with respect to time. Okay, so then now we are going to step 6. Okay. This step is actually we would like to differentiate both sides with respect to time. Okay, which is t now. Okay, so then now we would like to have take the derivative with respect to time of A equal to take the derivative with respect to time of L times W. Okay. Okay, so of course the left side I will have dA dt, and the right side here, then we have product, right? So we have to apply the product rule. So we take the derivative of L with respect to time times W plus L times the derivative with respect to time of the W then, okay? Okay. Then let us simplify this. So I will have dA dt is equal to W dL dt plus L dW dt, okay? And now we are going to work on the last step, step number 7. Now we are going to like substitute back the numerical info then. Okay. It is dA dt. What do we know? We know that L equal to 20 cm, W equal to 10 cm, dL dt is x cm per second, dW dt is 3 cm per second, which is equal to, okay, so let's plug it in. W is 10 multiplied to dL dt is 8 and plus L is 20 multiplied to dW dt is 3. Okay. So then of course to this one I will have 80 plus 60. The answer is 140 then. Okay. Okay, so then let's see what is the unit in this case. Okay, what is the units of dA dt? Okay. Then now you see that in this case 10 is in cm, and then 8 is in cm per second. So then in this case you will see that the unit will be cm squared per second then. Okay. And it actually makes sense to have centimeter square per second because we are looking for the area per time, right? Okay. Okay. And now let us look at the next example now. Okay. Now today's example is, as that's been said that right here, a spotlight on the ground shines on the wall 12 meters away. Okay. And a man 2 meters tall walk from the spotlight toward the building at a speed of 1.6 meters per second. Now, relate to, again, when I see this, I know that it's related to the derivative now. How fast is the length of his shadow on the building decreasing when he is 4 meters from the building then? Okay. Okay, so then let's see. First of all, maybe let us draw the diagram, okay, to see how we understand the problem then. Okay, so this is actually the wall. Okay, maybe in this case, I have a spotlight. This spotlight right here is actually is a 12 meter, okay, away from the wall. And then now, okay, and I have a man that is actually is 2 meter tall. Okay, and then he is walking this way. Okay. Then now, let's see. In this case right here, you will see that, okay, if this is the light, then now what happened to this one right here? This is actually is the shadow, right? Okay. This is the shadow. Okay. And now, same situations. Okay. Now, right now, what if the man is walking? So therefore, again, to walking toward the wall. Okay. Immediately you will see that what happened to the shadow. Okay. Well, the shadow right now is actually is decreasing. Okay. So therefore, it actually is makes sense that how fast is the length of his shadow on the building, right? Decreasing. Okay. When he actually walking toward the wall, is actually the shadow is decreasing. Okay. Okay. And now, how do we actually work it out this problem? Let's us look at this. Okay. So first of all, I know that the speed of the man is 1.6 meter per second. Okay. But this speed right here is what? Again, to this one right here is the change of this distance. Okay. From here to here. Okay. So therefore, in this case, if I assign this one to x, okay, that means in this case, the speed is how fast is this h changing then? Okay, so it will be dxdt is the speed of the man in this case right here. Okay, then now let us look at this. Now, what if I assign that the shadow is actually, I consider that this is the y values. Okay, okay. Then in this case, what I'm looking for. You see that to this one, it seems that the shadow is decreasing, okay, it's related to y. So in this case, I could make it dy dt is how fast is the shadow decreasing, okay. This is kind of like the idea, okay. So then now, let us write down now. So I would like to let x be the distance between the man and the spotlight. Okay. And now I would like to let y be the height of the shadow. Okay. Then let's see, what do we know? We know that dxdt is equal to 1.6 meter per second. And what we are looking for, we would like to find the dy dt. Okay. It's equal to what? When, okay. Now you see that in this case now, let's check it out. If we are looking for, okay, so again, when he is 4 meters from the building. Okay, so now if I'm looking for, okay, if this is 4 meters from the building, then what happened to X? If he is 4 meters from the building, meaning what? X is equal to 8 meters then, right? Okay, then now let's see how do we actually approach this problem. Okay, so what I will do is I would like to simplify the diagrams that I have here. Okay, so maybe let us consider that this is basically is a triangles. Okay, and then to this triangle right here, this is actually is 12 meter. Okay. And we don't know how high is the shadow, so I make this a Y right here. This color right here. And now the man is actually is 2 meter tall. Okay. And one more information is I know that the distance from here to here is X. Okay. Okay, so let's see how do we actually work it out this type of problem. Okay. Now to this problem, it seems that we could, okay, make this triangle right here to be two similar triangles. Small one and a big one. Okay. Then let us write down what information do I have. Okay. First, I know that this length right here is 12 meter. And then this side right here is Y. Okay. Another thing that I know is this one is 2 meter. And then this is X right here. Okay. Okay. Now, let's see how do we actually relate, again, work with this similar triangle now, okay? Okay, then let us review some of the things that we learned it before, okay? Now, if we have two similar triangles, okay? If this is A, B, and C, if this one is X, Y, and Z, okay, if this is the case. Then now, to this one, then if they are similar triangles, okay, that means in this case we could make the ratio, like for example, A to X is equal to B to Y is equal to C to Z, right? We could do it this way. Or if I want to, I could make this is A to B is equal to X to Y. Okay. Or if I want to have, again, A to C, then in this case, it will be X to Z then, okay? Something like this, okay? Okay, then now, let's see, how do we actually work this out here, okay? Now to this problem, we would like to find the dy dt. This is what we are looking for. So then to me, what I would like to do is maybe let us work with the ratio, then start with y, okay? Then we could have y to 12 is equal to 2 to x then. Okay, so then now, the easy way to do this one is I would like to solve for y because we want to find dy dt. Then maybe we could have y equal to 12 times 2 over x, which is 24 over x then. And now I would like to, after we create the equation, then we would like to take the derivative with respect to term of y, is take the derivative with respect to term of 24 times x to the negative 1, okay? We change 1 over x to x over 1 because 24 over x to 24 times x to the negative 1. It is easier for me to take the derivative, okay? Okay, and now let's see. So now I will have the dy dt is equal to 24 multiplied to negative x to the negative 2 dx dt then. Okay. So dy dt is equal to negative 24 over x squared dx dt. Okay. Okay. After we take the derivative, then what is the next step? The next step is we are going to input the numerical info now. So I have dy dt evaluate at x equal to 8 meter, and then dx dt is equal to 1.6 meter per second, okay? Which is equal to negative 24 divided by 8 square multiplied to 1.6 then, okay? Okay, then now let's try to simplify. 8 times 3. 8, this is 0.2. So the answer that I have, it will be 0.6. But this is a negative. Okay, so then in this case, I will have meter per second. Okay. So therefore, the shuttle is decreasing at 0.6 meter per second is weight. Okay. Okay, so then now let us look at the next example now. Okay, so then now an inverse pyramid is being filled with water at a constant rate of 65 cubic centimeter per second. Okay, and then the pyramid at the top has a shape of a square. Okay, so in this case right here, we know that these B1 and B2, they are the same. Okay. With the side of length 5 cm and the height is 15 cm. Okay, we would like to find the weight at which the water level is rising when the water level is 10 cm. Okay. Okay, so then let's try to draw the diagrams. Okay. Okay. So now this is a 5 cm here. This is a 5 cm. And the height of this is 15 cm. Okay. Then now, what we want to do is, again, I would like to maybe let me, okay. Now I would like to fill in a water at the weight of 65 centimeter cubic, right? Cubic centimeter per second. Okay. Okay. Now you will see that to this one right here, when we have the volume, okay, now 65 centimeter cubic, this one is related to the volume per second. So in this case, maybe let me assign that dV dt to this numerical information then, okay? And then now, when you fill in the water, what happened? The water level is rising, right? So in this case right here, maybe let us look at this, okay? So this is the water that I've being filled here, okay? Then to this one, if I add some water, maybe I let this is X, okay? And then now I would like to, the height of this, I call it H then. Okay, you see, the more you fill it in, of course, the H change and also the width of the water is also changing. Okay, so okay. Then now let's see how do we actually work it out this problem. Okay, so first step, I would like to let X be the width of the water, okay, being filled. Okay. And then I would like to let H be the height of the water level then. Okay. And now what do we know? We know that dV dt, the volume is increasing at a rate of 65 centimeter cubic per second. Okay. And now what we are looking for, we are looking for the water level. Okay, so I have changing, right? dH dt is equal to what when H is equal to 10 cm. Okay, those are the information that we have. Okay. Then now let's see, how do we actually create the formula to work it out this problem now, right? Then now we are looking for the volume changing. So meaning now what we want to do is we would like to find the water. That means the volume, right, of this water right here. Okay, this is the volume that we are looking for. So therefore, in this case, the volume of the water, okay, is equal to 1/3 x squared times h. Okay. Okay, then now what we want is we would like to have the volume is depend on only one variable, which is h. Okay. Then now let's see how do we actually get rid of this x now. Okay. Okay. So let's see how we actually work this out. So when what I would like to do is I would like to cut. Okay. Kind of like do it this way. Okay. To cut the perimeter this way. Okay. So then now the cross section is look like a triangles. Okay. Okay. Then let's see what information do I know about this triangles. First, I know that this width right here is 5 cm. And I know that the height of this is 15 cm. Okay, this is given. And then now, what I want to add is, okay, this is the width of the water, which is x. And this is the water level, which is h then. Okay. And then now, let's see how we work it out. The problem is, okay. because I would like to have the volume is depend on H, then now maybe let us start with X then. So X over H is equal to 5 over 15. Then I will have X is equal to, again, this one is 1, 3, right? So I will have H over 3 then. Okay, so that's good. Because we know that X is equal to H over 3, then now I will have V of H. That means the volume is depend on H is 1/3 H over 3 to the square times H now. Okay. Replace X with H over 3. Then H squared over 9 times H. So now I will have H to the power 3 over 27. Okay. Or it is easier for me to finding the derivative. So maybe just write it this way then. 1 over 27 multiplied to x to the power 3. Then now I would like to take the derivative with respect to time of v equal to the derivative with respect to time of 1 over 27 h to the power 3. Okay. And the left side I have dv dt equal to 127, and the derivative of h to the power 3 is 3h squared dh dt then. Okay. Okay. Then now let's see how we finish the problem. This is 9 right here. Okay. Then because I would like to solve for dh dt, okay, then maybe we could have 9 dv dt divided by h squared is equal to dh dt then. Okay. So I have dh dt evaluate at dv dt equal to 65 center cubic meter, cubic centimeter per second. And then we have h is equal to 10 cm. Okay. So which is equal to 9 times 65 over 10 squared. Okay. And now let's see how we work it out with the unit. So to this one here, then we have center cubic centimeter per second. This one right here, we actually have cm squared. Okay. When we cancel it, then I will have centimeter per second then. Okay. So then we know that the water level is rising at 5.85 cm per second. Okay. Okay, so this actually is a couple example related to related weight. Okay. Thank you.